Today we're going to be talking about visualizing fractions on number lines, and really being able to visualize what a fraction means is going to demystify a lot of those fraction operations. And fractions are going to appear all throughout your college career. It's a very kind of common feeling for people to bring into their college experience from previous school experience that they're perhaps a little bit afraid of fractions, they don't like to work with them, they're going to try to avoid them, but we're not going to do that. We're going to tackle fractions head on. And we're not going to be afraid of them. We are going to visualize them and we're going to understand what they mean. And really, at the basic definition, fractions are dividing a whole into equal pieces. That's really what it is. So if I have the fraction 1/4, that literally means 1 divided by 4. I have some whole and I divide them into 4 pieces that are each 1/4 big. That's really what I'm doing when I say 1/4. If I have 3/4 instead, what I'm doing is taking those same pieces and I'm grabbing 3 of them. That would be 3/4. That was a really messy 3/4 there, but I will write that to the side here. So I could grab 3 of them to give me 3/4. Or I could think that I have 3 pizzas. I want to divide them evenly between 4 people. Each person's going to get 3/4 of the pizza. That's what that really means. And what's going to help with that, so that you don't have to kind of draw these are kind of tape diagrams if you kind of like the boxes that are divided into things. But what might be easier is actually just kind of visualizing on a number line. And as you're practicing when you're practicing with the review exercises, this is what you're really going to be working with, are these number lines. So with these number lines, if for example you wanted 6/8, what you would do is mark between 0 and 1. You would divide it up into 8 equal pieces. You would have 1/8, 2/8, 3/8, 4/8, 5/8, and then over here you would finally have 6/8 here at the 6th mark, or 6/8 here on the one that was sort of pre-made and a little bit nicer than the diagram that I was making over here. Similarly, if you wanted 1/6, what you would do is break a number line into 6 equal pieces, and then 1/6 would be the first of those equal pieces. 3/6 would instead be right there halfway through at 3 of those 6 equal pieces. And so it's going to be helpful to be able to have this visual in the back of your head that anytime you're working with a number like 1/6, what you should be thinking is that between 0 and 1, I've broken up into 6 equal pieces, and that's at the first one. For a number like 6/8, between 0 and 1, I've broken it up into 8 equal pieces, and that is the 6th one. Always something that's worth keeping in the back of your mind. In order to compare fractions, it can be very helpful to visualize them on the number line. And as a sanity check, you can also think of it just in terms of the sort of breaking up a whole into parts metaphor. So for example, if you want to compare 1/3 versus 1/5, the number line way would be to draw 2 number lines between 0 and 1, 0 and 1, 1/3, 2/3 broken up into 3 equal pieces, 1/5, 2/5, 3/5, 4/5, and then 5/5 would be equal to the 1. And you would see that 1/3 is more to the right than 1/5. This is a part that's a little bit easier to see with technology to make sure you actually evenly divide it. But if you were, a halfway decent artist, hopefully that's what you wrote on your paper too. 1/3 is to the right of 1/5, so that means 1/3 is greater than 1/5. We read these inequality symbols left to right. Always eats the bigger number and points to the smaller number. You can equivalently say 1/5 is smaller than 1/3. 1/5 is less than 1/3. Another way to think about it is if I have a whole and I break them into 3 equal pieces, so if I have a whole pizza and divide evenly between 3 people, each of those people is going to get a greater slice than if I have a pizza and divide evenly between 5 people. If I've taken a whole and broken it into more pieces, each of those pieces has to be smaller. And that's always something that's worth keeping in mind. As a fun fact and a little tangent, A&W, the restaurant, once wanted to come out with a 1/3 pounder to compete with McDonald's 1/4 pounder. And people thought that meant that they were getting less meat. In reality, 1/3 of a pound is bigger than 1/4 of a pound. but people sometimes just think, oh, well, 4 is bigger than 3, a quarter is bigger than a third, and that's not the case. You want to think instead, take a step back and say, hey, if I break up a pound into 3 pieces, a third, one of those 3 pieces will be bigger than a fourth, one of those 4 equal pieces instead. I'm going to pause and I want you to take a second to try to do this comparison yourself. So play around with some number lines and see how these numbers compare. So if I'm comparing 1/2 versus 2/3, I'm actually going to come back to this diagram in order to compare it. So if I have 1/2, if I've broken a whole into 2 equal pieces, that's going to be bigger than 1/3, breaking a whole into 3 equal pieces. So because of that, that means that 1/2 is bigger than, I said in my head 1/3, I didn't read the problem, I was a bad student. It's bigger than 1/3, however, the problem asked about 2/3. So 1/2 is bigger than 1/3, but it's going to be smaller than 2/3. So if I take a whole, break it into 3 equal pieces, but then give you 2 of those 3 equal pieces, that's bigger than just 1 of those 2 equal pieces. So 1/2 is smaller than 2/3. Similarly, 3/4 versus 3/5. For here, you can think kind of conceptually, if I take 3 and I break it into 4 equal pieces versus taking 3 and breaking it into 5 equal pieces, which one do you think is going to be bigger? Taking 3 and breaking them into 4 equal pieces should be bigger than taking 3 and breaking them into 5 equal pieces. But we can also compare with these diagrams. So if I were to sort of throw in between here, 0, 1, for 1/5, it might look something like this. For 2/5 might look something like this. 3/5 might look something like this. And then for 4/5 might look something like this, and then 5/5 would be over here at 1. So it would indeed be the case that 3/4 is bigger than 3/5 as well. You can even do the math on your calculator if you don't believe me. If you do 3 divided by 4, that'll give you 0.75. 3 divided by 5 would give you 0.6. 0.75, 75 cents is bigger than 0.6 at 60 cents. So in that case, which we'll go into decimals later, but regardless in that case, 3/4 is going to be bigger than 3/5. This last one, got to be a little bit more creative to visualize, but if I take a whole, break it into 8 equal pieces and then give you 7, versus take a whole, break it into 6 equal pieces, give you 5. Or another way of thinking it is 7 things divided evenly between 8 people, 5 things divided evenly between 6 people. Which one do you think is going to be bigger? Well, this one, the number line can be helpful, but if I have a whole broken into 8 equal pieces, and I look at 7 of those 8 equal pieces, that's going to be a little bit bigger than a whole broken into 6 equal pieces, and I take a look at 5 of those. So in that case, 7/8 is going to be a little bit bigger than 5/6. Now, particularly for that last one, you might be thinking, I want a bit more of a systematic way than just looking at a number line. I especially don't trust myself to write a very nice, clean, beautiful number line in the middle of a test. You'll notice that I sort of use these pre-made diagrams just to make sure that I kind of drew this evenly, particularly for the ones that can be considered a little bit close to each other. So we might want to kind of convert between fractions and visualize equivalent fractions in order to help us out with that. And that's something we're working up to here. Now, before we jump into just instantly creating the equivalent fractions, we might want to take a moment to pause to deal with what if we have a numerator that's bigger than our denominator. And now I say that out loud, and I haven't actually technically gone over the biology of a fraction now, have I? If I have 7/8, the 7 up top, that is my numerator, and the 8 on the bottom, that is my denominator. So in all of these cases, my numerator had been smaller than my denominator. We were all getting parts of one whole, but sometimes fractions describe numbers that are a little bit bigger than 1, where I'm still doing this division, but perhaps something like 8/7 instead. How do I deal with that? Well, there's 2 different ways. You can have what's called an improper fraction or a mixed number. A mixed number can sometimes be a little bit easier for us to visualize what it means. So for a mixed number, that might be something like 2 1/4. That means I have 2 wholes, and then I tossed on a quarter, 1/4. An improper fraction is instead called improper because the numerator is greater than or equal to the denominator. So something like 9/4. Mathematically, 9/4 is actually easier to work with. So in a lot of your algebra, calculus classes, that sort of things, you're actually going to stick with just calling it 9/4. So mathematicians actually usually keep it as 9/4. But then whenever you're taking a step back and you want to put things a little bit more in context, it's going to help to then convert him to a mixed number because those mixed numbers tend to be a little bit more in terms of how we think. So how do you convert between the two? Well, in order to convert between the two, you want to actually just do the division. That's really what it boils down to, especially when converting improper fractions to mixed numbers. So what do I mean by do that division? So if, for example, I have 13 fourths, that literally means 13 divided by 4. So I'm going to do 13 divided by 4. I'm going to do it sort of the long way, but if you wanted to type it into a calculator, you would get something plus a decimal. You could figure it out that way too. So 4 goes into 13 3 times. 3 times 4 gets me 12. 13 take away 12 gets me 1. So that's 3 with a remainder of 1. Had you typed this into a calculator instead, you would have gotten 3.25. That would have told you that 3 would have been the greatest number that can go into it. And then you could have to the side done 3 times 4 is 12. And then 13 minus 12 gets you 1 to get you that remainder of 1. That would have been an alternate way using technology to do this. But I do encourage you to try it without technology because it builds that number sense. And that number sense is really going to be helpful for future coursework. So here, since this is 3 with a remainder of 1, that means 3 is going to be the whole number, and then 1/4 would be the fraction part. How did I know to put it over 4? Because we were dividing by 4 in the first place. So you're actually just going to keep that denominator the same. Same deal here. If I have 11/4, if I do 11 divided by 4, 4 goes into 11 2 times. 2 times 4 is 8. The remainder is 3. That's why we end up with 2 3/4 whenever we do that division. So in short, divide the numerator by the denominator. That's the definition of the fraction. The quotient is this number that's up here. So that's what you got here. The quotient is kind of the whole number, the most number of times it goes in. That becomes the whole number similarly on your actual fraction here. And then the remainder becomes the numerator of the fraction. The denominator stays the same. So I'm going to go ahead and pause. Go ahead and try that with these two improper fractions to convert them to a mixed number, and then come back to this video. So for 9/5, for example, if I do 9 divided by 5, 5 goes into 9 one time. 1 times 5 is 5. 9 minus 5 is 4. So that means I have 1 with a remainder of 4. So that means this converts into 1 whole with 4/5 left over. Similarly, if I'm doing 17/4, I've already used that bright blue quite a few times. So let's go and change that up a little bit. 17 divided by 4. 4 goes into 17 4 times. 4 times 4 is 16. 17 minus 16 is 1. That is 4 with a remainder of 1. So 4 1/4. Because again, that remainder goes in the numerator, that 4 goes in the denominator. The other way around is also very helpful as well. So before we were doing division to create the mixed numbers, we're going to use multiplication to work the other way around. So if, for example, I have 2 3/4, what I'm going to do is take my whole number 2 and multiply it by that denominator 4, in this case to get me 8, and then you're going to add the other original numerator, in this case 3, to get you 11, and then you're going to keep that same denominator to put that over. So let's take another example of this. So for 3 2/5, here I'm going to multiply the 3 times the 5 to figure out that basically 3 wholes is the same thing as 15/5. That's really what I'm saying when I'm doing that. So I'm figuring out, okay, the whole number 3, that's the same thing as 15/5. Then I'm going to take that 15/5 and that original 2/5 that was also part of that mixed number to get a total of 17/5. If I have 15/5 and 2 more fifths, that gives me 17/5. Similarly, for 5 1/3 and 4 3/8, go ahead and pause your video to see if you can convert those two. So for 5 1/3 and 4 3/8, for 5 1/3, I would do the 5 times 3 to get me 15/3 that I'm really dealing with, plus the additional 1 from the 1/3 gives me a total of 16/3 as a improper fraction. Similarly, for the 4 3/8, I'm going to have 4 times the 8 to give me 32/8 plus the 3 from the original 3/8 for a total of 35/8 for that 4 3/8. For all of these, a lot of these are not necessarily written in what you would call simplest form. And in order to visualize simplest form, we have to have this idea that there can be equivalent fractions. So for example, you do have it the case that I could divide a whole into 2 equal pieces and have a half. Could divide a whole, divide into 4 equal pieces and give you 2 of them. You still ultimately are getting half of them. Have a whole, divide into 6 equal pieces, give you 3 of them. You'd still have a half of them. Or take a whole and divide it into 8 equal pieces and give you 4 of them, you would still have half of them. Now, how would you figure out that these are all equivalent fractions? Well, you can literally visualize this, or you can be a little bit more systematic and simplify. So conceptually, what you would ask is, can we multiply both the top and bottom of one fraction by the same number to get the other fraction? Which is a similar question to systematically actually simplifying both to their lowest terms. So let's see for a second what we mean by that. So if we're asking, is 2/3 equivalent to 4/6? Conceptually, what you might ask yourself is, hey, I notice if I do 2 times 2, I get 4. And if I do 3 times 2, I get 6. So 2/3 is equal to 4/6. That's a great conceptual way to think about it. If that wasn't immediately sticking out to you, the more systematic way you can do it is simplifying both of these fractions. So for 2/3, I want to see if there's something I can divide both the top and the bottom by. In this case, the only thing that's both of those are divisible by is 1, so 2/3 is already simplified. However, 4/6, if I check if there's something I can divide both the top and the bottom by, I can divide both the top and the bottom by 2. 4 divided by 2 gets me 2. 6 divided by 2 gets me 2/3. Oh my gosh, they must be equivalent fractions. So let's practice that skill a little bit. So if I'm going to practice this skill a little bit more, if, for example, I'm comparing 3/4 and 9/12, I may initially notice a pattern. Or if I want to systematically simplify, for 9/12, 9 can be divided by 3, 12 can be divided by 3, and lo and behold, I'm actually left with 3/4. I may have similarly noticed that 3 times 3 gets me 9, and 4 times 3 gets me 12. Either way, I have noticed that these fractions are equivalent. For 24/66 and 21/30, to me these aren't instantly sticking out that I can multiply one by the other to get the other. So let's just try simplifying both of these. So if I take 24/66, I may notice that they're both divisible by 6. 24 divided by 6 gets me 4. 66 divided by 6 gets me 11. For 21/30, I may notice they're both divisible by 3. 21 divided by 3 gets me 7. 30 divided by 3 gets me 10. And now 7 is prime and 11 is prime, so neither of these can be broken down further, and they're not the same thing. So my gut that there was nothing that was really sticking out, that these could multiply into one another, was kind of correct. These are not equivalents. For this next one, you may notice a pattern for multiplication. In particular here, I do notice that if I do 55 times 2, I get 110. And if I do 143 times 2, I do get 286. Or if I had been a little bit more systematic, I could have worked the other way around. If I have 110 over 286, I'm personally sitting here thinking, well, the only thing I know is both of these are even, so let me try to divide both by 2. 110 divided by 2 does get me 55. 286 divided by 2 does get me 143. And then the moment I notice that they are the same number, I can go ahead and say, yes, these guys are equivalent. If a fraction is in its simplest form, that means that there's no more numbers that they have in common, basically. And by they, I mean the numerator and denominator. It is completely fine not to instantly recognize, for example, for 8/24, you could have instantly recognized that both of these are divisible by 8 to get you 1/3. That's great. Or you can just keep on dividing till you can't anymore. So if you're that's a lot of thinking, what I do notice is 8/24, hey, they're both divisible by 2. They're both even. Great. Divide both by 2. Oh, they're still even. Divide both by 2. Oh, they're still even. Divide both by 2. Great. Now I'm down to 1/3. That's a completely okay way to do it. Whichever way floats your boat, go for it. So you can either instantly recognize what's the biggest number that goes into both. Let me divide both by that. Or just keep dividing till you can't anymore. Either way is a-okay. So let's practice that a little bit. So if I have 20 over 36, I might just initially notice, hey, these are both divisible by 2. So that becomes 10 over 18. And hey, these are still divisible by 2. That becomes 5 over 9. As far as I know, there's nothing that goes into both 5 and 9. That would simplify fully to 5/9. Alternatively, I could have instantly divided both by 4 and I would have gotten the same thing. For 210 over 270, I'm going to think that probably the dividing multiple times is going to be the simplest. And my hint to you is probably 10 goes into both. So why don't you try to simplify this and then restart the video whenever you have. So here, since they both end in a 0, they're divisible by 10. I get 21 over 27. Now these are both divisible by 3. As a pro tip, actually, if the integers in the number add up to a multiple of 3, so 2 plus 1 is 3, 2 plus 7 is 9. If those add to a multiple of 3, then it's divisible by 3. So that gets us 7 over 9, and I believe that is as simplified as we get. For something like this last one, you're going to want to make sure that you actually simplify the numerator first. So 1 plus 10 is 11 over 4, and I would say that's already fully simplified. If you were really motivated and you want to write him as a mixed number, 4 goes into 11 2 times. 11 minus 8 is 3. That would be the same thing as 2 3/4, but you don't have to do that.